Yes, I did my PhD in Barcelona, and the research that I am going to present was done there. But currently, I am working as a postdoc at KTH, Royal Institute of Technology in Stockholm. My research is focused on the design of vast networks with regard to the evolution of the urban dispersion. First, I'm going to present the motivations of this research and the general question that I wanted to answer. Then I will try to explain. I will explain the theoretical analysis in order to answer the previous question. In the third section of this presentation, I will show a specific case study where we try to check the previous conclusions, and finally, I will emphasize the most relevant results. In the literature, we can find a discussion about how planners have to design the vast networks. In our cities, in general, planners try to design the networks reducing to the minimum expression the minimum of the number of transfers. They consider that transfer is a very negative step of the transit chain, and then we have to connect most origin destinations by direct trips. It has a certain consequence. For example, we need a lot of lines. The resultant networks are diffuse systems that don't work as a network, as a real network. If not, they work as a group of lines, each one independent to the others. And with evolution or cities, where cities tend to more dispersed scenarios, more complex mobility patterns, the necessity to connect more origin and destinations, then we will need more and more lines. The result of these designs is that we have a lot of resources that disperses among many lines. Then we cannot reach high frequencies, and the readability of this network is too low, and users cannot take advantage of all the resources invested. Then some authors propose a change on the design, working with simple structures, where with a small number of lines we try to connect, we try to coverage all the city, where we focus all resources in a small number of lines, characterized by high frequencies and a high readability for users, but they have a problem. We will need to make transfers. And this is the comparison of these two design approaches is made I try to compare this type of design approach to know if a change of the design from direct trips to transfer connections could be a good solution. If we simplify the urban form evolution in this way, initially I have a city with a strong center where all activities are located, and progressively the city evolves to more dispersed scenarios where the activities are located in external areas of that center, initially in the surroundings of that center, and progressively in areas farther away from the center. The question is how we can satisfy the mobility patterns associated of the different stages of urban form evolution. Initially, a radial network could be a good solution because it's a cheap structure, it's a cheap network for the agency point of view, and at the same time satisfy the centripetal vector of displacement. But what happens when new areas and traction areas appear in the city? Then if we follow the first design approach based on direct trips, we will try to connect the new areas by additional lines that we implement over the pre-existing radial system. and progressively more and more lines. And the question is if there is a certain degree of dispersion from which the best solution is no longer the introduction of new lines, if not the best solution is to change the design approach, no? From direct connections to transfer trips. And I tried to answer this question initially by a theoretical analysis. I worked with analytical model based on continuous approximations and geometrical probability. It's a useful type of models to obtain general insights about the behavior of transport systems. I idealized my city as a square city characterized by a grid street pattern, only vertical and horizontal streets. And I assume a spatial demand distribution to represent the previous simplification of the urban form evolution. I worked with two parameters, the parameter phi that determines the size of a central area where all the destinations are located, and then a factor fd to distinguish the density of origins in the central area and in the rest of the city. In this way, I can balance the participations on the mobility of the center and the periphery. Atop this street pattern, atop this city, I compare an additional group of lines to guarantee that the different ways where I divide the central area are connected with the whole city. And two different transfer-based structures. A hybrid network where I have a grid in the central area of the city, and the branching of the corridors, of these central corridors, cover the rest of the periphery, or a complete grid where the balance between the resources in the center and in the periphery is based on the different headway of service between the corridors that cross that central area and the corridors that only cross the periphery. Then my model optimized the different structures, minimizing the total cost of the system, where I consider agency cost, the infrastructure length, the vehicles kilometers traveled, and the fleet, and the different components of the user transit chains, access, waiting, in-vehicle, and transferring times. Subject to different constraints, physical constraints, or the most relevant, the constraint of the occupancy with regard to the capacity of the vehicles. For each structure, I obtain the optimal configuration, and then the structure that has the cheapest cost is the most convenient to serve to satisfy the mobility in a specific city with a specific dispersion degree. Then after the model, I obtained different results. I worked with a idealized city where I defined the input parameters, demand, different parameters of operation like the speed, the capacity of vehicles, the dwell time. And then first I get results from a scenario where I only worked with the parameter phi between 0 or close to 0 and 1, while the parameter fd remains equal to 1. I only consider initially the size of the central attraction area. And I observed that the total cost of the system for all the structures grows with the dispersion, but not in the same way. A radial network could be a good solution for a high centralization when phi is close to 0, but immediately the cost grows a lot with the dispersion. A direct trips could be a solution for intermediate scenarios of dispersion, but the the slope of the total cost curve with the dispersion is greater than the transfer options, the transfer trips options, then there is a certain degree of dispersion from which the best alternative or the cheapest alternative would be to work by transfer trips. And this happened for total costs, but also if we compare a transfer-based structure with direct trips. For the agency, would be cheaper and also for users. Okay? The introduction of transfer gets a better balance between the different components of the transit chains to reduce the total travel time. Here I show the different components of the travel time with regard to the dispersion for different structures. A radial network, the number of transfers in a radial network grows sharply for the first scenarios of dispersion, but the main inconvenience with regard to the rest of the structure is the length of trips, because all the trips pivot on the central point of the city. Direct trips remains, the number of transfers remains equal to 0, but the users lose spatial coverage, or the frequencies are higher than, for example, in a transfer-based structure, where transfers are high, the percentage of transfer is high, but they get a better balance with regard to the rest of costs. Then I introduced in the analysis the factor, the parameter FD, and obviously that the cost, the total cost for the different structures decrease because I have more central tips and the periphery has a less presence in the mobility, but the decrease is similar in all the structures. Then if we obtain a diagram of application for the different network structures with regard to parameter phi of and FD, we observe that the value of phi of change between structures doesn't change significantly, although FD is higher. And with this analytical model, I can get a first approximation of the applicability for the different structures, that diagram of application, of area of application, and could be a first or a tool to get a first approximation about planners have to design or have to focus face the design of this of the bus networks, and then I wanted to translate these results to a real case. No. The first, in my model, I assume a monocentric structure where certain spatial autocorrelation, and my city works as a whole city. No, okay. People wants to go from any region to any destinations, and the gravity of the mobility is coincident with the mobility, the center of gravity for the mobility of the different districts of the city or different zones of transport. I don't have a city that works as independent districts. And the second question is how to measure the dispersion in the city. No? The urban sprawl process has different dimensions, but I estimate or I calculate two of them, concentration and centralization, because they are the more extended in the literature. For a concentration, I use a Gini coefficient, and for centralization, an area-based centralization index, and I connect these real measures in the city with the parameters of my model. If we compare the Lorentz curve in a real city and the Lorentz curve in my spatial demand distribution, we can get these equations where I can obtain the value of the parameter phi in a city, knowing the Gini coefficient for the attracted trips and the factor FD with the Gini coefficients for generation and attraction and the value of phi. And the same for the other index. And I apply this for Barcelona. Barcelona has a clear center, a strong center. It's a monocentric city, especially for the traction trips and mobility and work as a whole, because the mobility for different sources around the global mobility and inside this center. Then I estimate the values for the Gini coefficient and the centralization index, and then the values of phi. And I determine the diagram of applicability for the different structures for this city, knowing the characteristics of Barcelona. And we observe that the values of 5 in this city are in the area of application of a transfer-based structure, a hybrid structure. Then now we try to redesign the bus network for Barcelona, thinking with a transfer structure. This is the previous network in Barcelona. It's a complex network with a high number of lines, only urban lines 63, then we have to add neighborhood lines and some interurban lines. This is a typical direct trips based structure where we have many lines and we have many resources, but there are many lines with very low headways, and only 20% of line carry 50% of demand. We have many lines that don't have, they are not used too much by the users. And only 11% of trips are transfer trips. We assume that this is optimizes enough direct trip-based structure, and we try to compare this network with a new network designed thinking in transfers with a simple structure. We use the previous model to design a vast network for the core of Barcelona, for the city of Barcelona, because the municipality of Barcelona is a small city, 100 kilometers square. And we obtain results in two different scenarios. The commercial speed in the bus of Barcelona is too low, only 10 kilometers per hour. And in one scenario, we try to improve the commercial speed, and in the other, we try to improve the commercial speed. Then we need to implement operational measures, and the council said, okay, but we have to introduce a constraint on the design, only 11 corridors. We cannot develop this new network in more than 11 corridors of the city, because if not, the effects to the private vehicle would be too negative. And another case is when we don't consider the possibility to increase the commercial speed, and then we don't have a constraint for a constraint in the extension of the new network. This was the network for 11 corridors. We had only 200 kilometers, and it's a short infrastructure length where we can implement operational measures. But the problem of this network was that many areas of the city were far away from the new lines. Then we had to maintain a high number of the old bus systems working together with this new network. And the other option was a complete grid that has a better spatial coverage, 28 corridors. Obviously, the length, infrastructure length is longer, and the commercial speed is lower. But we can remove most of the old bus system. We did different simulations, considering only initially the bus demand, and we assigned the demand in these two scenarios, the previous pre-existing scenario, a scenario with 11 corridors and some of the old lines, and a scenario of 28 corridors. And we observed that the total travel time decreased around 9% in both cases, but in this case especially for the in-vehicle time decreased due to the higher commercial speed, although the users have to walk a longer distance to get to access to the public transport system. In this case, the access cost is shorter, but we cannot get to reduce the in-vehicle travel time a lot. And we did the same simulation considering the metro system and the demand of the metro system, then the total demand of public transport, and we observed that we also improve the total travel time. Then the second option, the 28 corridor, was the network chosen for implementation in Barcelona. This is a slow process because the agency didn't want to implement the new network in one day. Then they started a progressive process that has not finished it yet. But last 2 years ago, we had around 13 lines, and then we tried to analyze the network effect in this new network, because one of the most important factors for this type of networks, if there is interaction between lines, if there are transfer trips between the different lines of the new network. Then in 2016, the new network was this. We observe a clear map where we can observe the transfer points. The agency made a huge effort to translate well how people had to make transfers in the new system, with maps at the stop where indicate the way from one stop to the other stop. The information with what lines you can make transfers, or even information on the street to follow the path between stops. We had 3 different phases of implementation: 5 lines in the first year, 5 lines in the second year, and 3 lines in the third year. And in general, the implementation of one line implied that one old line was removed. Then we had at the same time working a network based on direct connections and a network based on transfers. And we wanted to analyze the evolution of the demand of the new networks. We observed we had the number of validations for the different lines per month, for the different new lines, and we observed that the total number of validations grew with the implementation of more lines. But also, if we observe the total number of validations only of from the lines of the phase 1, we observed that this number grew in the second phase and also in the third phase, and we wanted to obtain a relationship between this growth in the number of validations with regard to the implementation of new lines. Because this happened, this growth happened in the phase 1 lines and in the phase 2 lines, while in the remainder mode of transport the demand was practically constant. Then we did a very simple regression model where we tried to relate the number of validations with regard to the one transfer trips that depends on the length of the line that we are analyzing, and one transfer trips that depends in the length of this line, but also in the length of the line that have a common interchange point. In this way, we can distinguish the number of validations that come from direct trips and the number of validations that come from transfer trips. As users validate and in the first vehicle and in the second vehicle, we remove a half of the validations of one transfer trips to obtain the demand of the new lines. And we observe that the percentage of transfer trips in 4 of the lines, of the phase 1 lines, reached in the third phase a 20% of the total trips. That is very or higher than in the old system that was only 11%, and the prognosis in the last phase would be a 44%, almost the metro system. And we observe that if we compare the demand of the old lines that these new lines replace, we observe that the demand now, or after the third phase of implementation, the demand of these new lines is higher than the demand of the old lines. Then we can conclude that these lines are working well and they are attracting transfer trips. Then people are accepting this kind of trips when when a direct trip-based structure or the old network pre-exists, competing with this new lines. Then the first question, there is a certain degree of dispersion from which the best solution is to work with transfer trips was answered by the analytical model, and this could be a good tool for a first approximation about what kind of design approach planners have to follow in a specific city. And then the application in Barcelona shows that by simulations, a reduction of 9% of total travel teams we can get with this new design, and the new network are reaching a 26% of transfer trips in comparison with the 11% of the old system. And this is all. Thank you for your attention.
Any questions for this last presentation? Could you evaluate the environmental impact of your
we didn't evaluate. It's true that the objective is to reduce the number of vehicles in the future fleets, but initially this is a bit complex because it's not easy to remove the drivers. Probably in the future, when drivers retire, the new drivers won't be hired, and also because the agency is very conservative, and initially they don't want to reduce the fleet, but probably in the future, if the conventional lines or the pre-existing lines that will remain in the system, if they carry low levels of demand, they will remove. But
you showed on your charts there was a usage chart. Do you have also a feedback on user perceptions, like Christophe just testified on building energy efficiency?
The user perception with the change, it's true that the agency did different surveys, and it's positive, the change. In most of cases, the people say that they appreciate the new design and they appreciate the new lines. But I didn't work in that part of the project, that I don't have.
Okay, thank you very much.
Thank you.
We can applause.